Hello everyone, I am Fatima Mir Emi and today I will be presenting my solution for the data synthesis machine learning task second round. This task involves explaining different algorithmic concepts and their relevance to real world application, especially in distributed system and machine learning context. Let's go through each question one by one. Question 1, we can say outline an algorithm for finding a minimum spanning tree in a distributed system. Follow up, in what real world ML scenario would you use MST? Here we can see to find a minimum spanning tree in a distributed setting, I choose Borovka's algorithm. It's particularly suited for parallel and decentralized computations. How it works: each node starts as its own component. Each node finds the smallest edge that connect it to another component. All selected edges are added simultaneously to merge the component. This process repeats until we end up with one connected structure, the MST. Why Borovka's algorithm works well to distributed system? First of all, each machine can process its local edge independently. Secondly, only minimal computation is required between machines in each iteration. This makes it efficient and scalable for large networks. Machine learning relevance. MST are used in sensor network for building efficient communication paths, feature selection to detect redundant features based on correlations, image segmentation for merging similar pixel clusters efficiently. In the second question, here is given a large stream of user interactions, design a data structure for big O log n, range some queries and updates supporting both exact and approximate aggregation for downstream feature generators. Follow up, how would you parallelize updates for distributed feature stores? Here for handling continuous data stream where we need range sum queries and updates, I recommend two data structure. One, Fenwick tree, which provide big O log n updates and queries. Secondly, segment tree, which is more flexible, especially when merging multiple ranges or enabling parallelism. For faster approximate result, we can use count mean sketch or quantization, useful when exact precious isn't necessary and speed matters more. In a distributed setup, we can split the data stream by time or region. Each node maintain its local tree. Then we use frameworks like MapReduce or SparkReduce to merge partial result efficiently. Lastly, techniques like lock-free updates and key-based shardings ensure scalability and prevent data conflicts. In third question, we can see here, you were tasked task with designing an ML model cache, explain how a splay tree helps optimize access pattern and what the trade-offs are compared to LRU cache. Follow up: when would splaying harm latency in serving predictions? Splay tree overview. Imagine we are serving multiple ML models, maybe one per customer, and we want frequently used model to load faster. A splay tree can help here. It's a self-adjusting binary search tree that moves an access node to the root after each lookup. This ensures frequently accessed model remain near the top, reduce each time. Let's compare with splay tree versus LRU cache. Expects adaptability. In splay tree, learns access pattern dynamically, but in LRU cache uses fixed size, evicting least recently used item. Time complexity. In splay tree, uh, it is big O log n, but in LRU cache O1 using hash plus linked list. Memory uses. Memory uses in splash tree is lower, but in LRU cache it is higher due to extra overheat. Predictability. In splay tree it is variable latency, and in LRU cache stable and predictable performance. However, in real world prediction system, frequent rotation in splay tree can cause unpredictable delays. So, if consistency and low latency are more important, an LRU cache is usually the better choice. Last question: build a system to support efficient merging and query of connected user components in a social graph as edges are added or deleted for clustering in ML. Follow up: how does union by rank and path comparison speed up large scale ML graph operations? For this, I use the disjoint set union or union find data structure. It's perfect for tracking group of connected user in a social or network based system. How it works: each user start in their own set. Secondly, when two user connect, we use the union operation to merge their seats. Lastly, to check if two users are connected, we use the find function to see if they share the same root. Optimization. Firstly, union by rank. Attach smaller tree under larger one to keep balance. Secondly, path comparison. During find, directly connect nodes to their root for faster future lookup. This make both union and find nearly constant time. Constant time like this big O alpha n similar as O1, which is extremely efficient for large scale graph. Application in machine learning, graph clustering, or community direction. Secondly, we can say connected component labeling in image. Lastly, we can say in incremental learning for user group update in recommendation system. So in summary, we can see we can tell about the whole question as Borovka's algorithm help build distributed MST efficiently. Then Fenwick and segment tree handle range queries or stream data. Split tree offer adaptive caching for ML model but trade predictability for flexibility. DSU efficiently manage connected user component in network-based ML system. Each of these algorithms not only demonstrates strong algorithmic understanding but also show how classical data structure can be applied in modern machine learning infrastructure. Thank you for watching my presentation on the DataSynthis ML task second round. I hope this gave you a clear overview of my problem solving approach and understanding of distributed and adaptive algorithm in ML systems.